And let me share my screen. All right, so what do I mean by improper integral? So improper, first off, recall that the fundamental theorem of calculus says the function is continuous over the interval that you integrate. So if I'm integrating from a to b, the function must be continuous there. That includes things such as a function going off to infinity or having a sharp change in its slope. So if you look at this example here that's given, if we look at the graph, this function, 1 over the square root of 3 minus x, if I plug 3 in for x, I get 0 in the denominator. And one thing that I always enjoy about calculus is that in every math class up until now, you're basically told you can't divide by 0. It's still forbidden, but we now can give meaning to it. So if we have 1 divided by 0, that means that our function is typically shooting off to infinity. So you notice the curve, all of a sudden, right around 3, just starts going up really rapidly. Now it's never going to touch that line, right? That is an asymptote. And so the question is it possible for us to calculate that area, or is it infinite, right? Because we can never touch that line and close the gap. And that's not always something that you can just answer by looking at it. So in this case, the bound 3 is what causes the integral to be improper. So we're looking for, is the function continuous at either the bounds given or somewhere between those bounds? And so the way we have to treat this is, instead of integrating from 0 to 3, we have to replace 3 with some constant c and apply the limit as c approaches 3. And then up here, notice it says that if you actually approximate this integral using fni and t, it tells us that we get back a number, right? 3.46 something. So it looks like it's convergent, which means it gives us back a number, and it's not divergent, which means that it heads off to infinity or does not exist. Does not exist is going to, one of these problems will come out as, and it basically means that we have some relationship of infinities that we can't describe. They don't mean anything to us. Right? Infinity is a very strange quantity. So what kind of improper integrals can we have? So as I said, we can have ones where there's a discontinuity at the limit of integration. So here I've got 0 to 2. And you notice in this function that if I plug 2 in, 4 minus 2 squared is going to give me a 0. So that means that the value of 2 has to get replaced with c. So that's one type. We can also have one where our limit of integration is actually an infinite value. So this one here, we run from 1 to infinity. Again, we can't necessarily plug in infinity, so we have to rewrite it as the limit as a constant approaches infinity. So just notice this little guy here. See if I can fix him. Got the little spinning wheel of death all of a sudden. There we go. That should be a C up there. There we go. All right, and this one I also would I changed it on, I guess, a different form. I must have not saved it on this drive. This one here says an internal discontinuity, but in fact, this one is that both of these limits cause problems. So let me just give you an example of an internal discontinuity. I could do it with this second one here. If instead this integral ran from, say, 0 to 3, and let's just not worry about the square root for this example. So 2 is still a problem, but 2 is not one of the bounds. It occurs between the bounds. So that's what we would call an internal discontinuity. So we would need to write this as two separate integrals. We would need the limit as c approaches 2, and we would go from 0 to c. And we would add to that another limit, and we would need a different variable, d approaching 2, from d to 3. And so that's a property of integrals that you should remember, hopefully, right? That I have an integral that runs from 0 to 3. Well, I can break it up at any point between 0 and 3 and make it two separate integrals, and it still should give me the same solution. So are there any questions about what it means to be an improper integral? All right, so I'll go ahead and demonstrate. Either you're not certain yet, or less likely it made 100%, or you have 100% understanding. So let's go ahead and try one. So I'm looking at this problem here, and it should be clear that if I plug the bound 2 into the original function, that I would be dividing by 0. So that's my problem child here for this problem. And so I need to introduce a limit, and then integrate from that constant up to 5 of the integral. So then I'm actually going to go ahead and solve the integral by itself. And then come back and replace that answer. So how do we solve this guy? Any ideas?
U sub, make u equal to x minus 2.
Okay, so let's let u equal x minus 2. Du is going to be dx, right? So then this integral is du over the square root of u, which is u to the minus 1/2. Right, it's a square root that makes it a 1/2 power, and because it was in the denominator and I'm moving it to the numerator, it becomes a negative power. When you integrate, you add 1 to that, so that's going to be u to the 1/2, and you would divide by 1/2, but dividing by a half is the same thing as multiplying by 2. Now, technically, I would have plus some constant here because it's an indefinite integral. Let's replace u here. U is equal to x minus 2. And so I'm concerned with this piece right here. I will go back to the top. And I'm going to use that result now. So I have the limit as c approaches 2 of 2 times x minus 2 to the 1/2 evaluated from c to 5. So I plug in 5 first, and that limit does not apply, right? Because it doesn't have a c there. So I don't need to write it for the first part. I am also going to bring this 2 out in front of everything. So it's 2 times. Plug in 5. So 5 minus 2 to the 1/2 minus plugging in the lower bound. In this case, we need the limit as c approaches 2 of c minus 2 to the 1/2. So what happens to the square root function as c approaches 2?
It gets closer to 0.
It's going to go to 0, right? So this whole thing just becomes 0. And we are left with 2 times the square root of 3. So most people will look at this problem and go, well, that was silly, because if I had ignored the fact that it was improper and just plugged 2 in there initially, I would get the same solution. That does not always occur, however. Let me see which other ones here I would like to do for you. So these two have infinite bounds. I guess I'll do B. I'll leave C for you guys. Okay. So this time I have an infinite bound, so I need to rewrite this guy as limit c approaches infinity, integral 1 to c, and I leave the inside alone. It's a good thing it starts at 1, right? Or else we'd have problems at, say, if it started at 0, right? We'd be dividing by 0. So we'd have another bound that caused problems. But we don't have that here, so that's good. So now again, I want to go ahead and just go off to the side here, solve the integral, and then come back. So how would I solve this integral? Any ideas?
By parts.
I think we could, but I don't think we need to.
Use substitution for u equals 1 over x.
Okay, so let's let u equal 1 over x. What's that make du? If I rewrite this way, it might help. It would be this. We've got the minus 1 over x squared there, or we've got the 1 over x squared. We just need a negative sign. Right, I could rewrite that integral as e to the 1 over x times 1 over x squared dx. And I could introduce a negative there and put 1 out there. So this is negative e to the 1 over x is going to be e to the u, and everything else is du. And that's our favorite integral because it just comes out as e to the u. Substitute that back in, and we have this. Again, I'm only interested in this piece. I don't need the constant because I actually have bounds. So I would come back up here and say, okay, this is now the limit as c approaches infinity. And I've got minus e to the 1 over x evaluated from 1 to c. So that is going to be limit c approaches infinity. Ooh, that looks terrible. Of minus e to the 1 over c. And then we always subtract the lower bound. So this would be minus a negative e to the 1 over 1. So the second part's really easy. That's plus e. The question is, what happens to this limit? So that is an exponential. So what does that look like? So a normal exponential would look like this, right? So what do we think that one would look like?
Would it slope downwards because of the negative sign?
Do you mean start up high and then decrease?
Maybe.
So I think that would be if we had e to the negative power.
Oh. Oh, okay.
So I'm just gonna go ahead and plot this for us. And what are we approaching? Infinity, right? So maybe I better plot this a little farther out. Okay, so I plotted this on Mathematica. Ooh, that's not what I wanted. I thought that was going to be a picture. There we go. This is what our exponential looks like. But it doesn't want to. There we go. So negative e to the 1 over c looks like this. I've only plotted out the 100 terms, but you can see that it's leveling out. And what number does it look like it's approaching?
1.
Looks like
-1.
negative
1.
1, right? So let's think about this. Forget about the negative sign for a second. What happens if I do 1 divided by infinity?
It approaches 0, and anything to the 0 power approaches 1, and then the negative sign.
So yeah, this would be e to the 1 over infinity, which is really e to the 0. And e to the 0 is 1, and there's a minus sign. So that's our final answer for that guy. So any questions about that?
Can you please scroll up? Can you please scroll up a little bit? Thank you.
Mm-hmm. Can you guys see the Mathematica page that I have up?
No.
So I just wanted to show you that when I ask the computer algebra system to do the same calculation, that it too says I'm not crazy. And gives us back e minus 1. So I asked it to integrate the same function from 1 to infinity, and it returned e minus 1. All right, I guess maybe I'll do one more of these. I'm trying to remember which one of these. One of these was interesting. This one here is a good practice for you. If you're, this looks like this is going to be a by parts integral. So not only is it improper, but it's also by parts. So these are all kind of good review problems for you because they make you do all kinds of different types of integration. This one looks like a basic U sub. This one's, sorry, this is partial fractions. I think I said by parts. Partial fractions. This is by parts. This one we've done many times now. So maybe I'll just do this one because it's got both bounds are infinite. So this one, you would need to make a limit as c approaches negative infinity. And because they're both infinite, we have to choose something in between. And the obvious choice here would be 0. The reason for that is this function x e to the x, it doesn't misbehave at 0, right? It has no problem if you let x equal 0. And that's always the easiest one to plug in. And then we would need another one for infinity, and we would go from 0 to infinity. So before we had a single bound that was a problem. We just replaced that bound. We also had in the previous example where, or so that was an infinite bound. And then this time we've got the situation where both bounds are infinite, so we had to break it up into 2 parts. And I guess maybe I'll do E as well for you. All right, so first we need the integral. We've already done this one. We would let u equal x, du equals dx, dv is the leftovers, v is the integral of dv. So plug in. This is x times e to the x minus the integral of v du. And that's a simple integral. It's our favorite one probably, besides maybe integral dx. Again, we only care about this part. So once we have that result, we can plug it in the part above. Okay, so I'm bringing this down now. So I need the limit as c approaches negative infinity. I'm going to go ahead and just plug in. So I would plug in the top bound first. And actually, before I do that, let me rewrite this as e to the x times x minus 1. So I just factored out e to the x there. And I did that for a reason. So let's go ahead and plug in. This is going to be e to the 0. Ooh, what happened here? E to the 0 times 0 minus 1. Then we subtract the lower bound, which would be the limit as c approaches negative infinity. We're plugging in c now. So this is e to the c times c minus 1 plus, same answer for this integral, but we're now plugging in first infinity, or we need the limit as d approaches infinity. I realize I should have had a d there, sorry. E to the d times d minus 1. And then always subtract the lower bound, which in this case is 0. So e to the 0, 0 minus 1. Did I leave anyone there? Please tell me if I did. Don't be shy. So again, I can only see so many of you, so I can't necessarily read everyone's face. Some of you look like I just killed your puppy. Got a John Wick situation going on here.
It makes sense.
Okay. So then, let's see. E to the 0 is 1 times a -1. This whole thing is -1. Over here, we have the same thing, but a minus sign in front of it. So this times this is going to give us +1. So these two things will cancel one another. So now we just have to deal with these limits. So there is a reason that I broke them into two parts. So just like the last problem, right, when we're evaluating limits, we could look at the graphs of the function. Another way to look at it is we've got an exponential function and we've got a linear function. Which one of those grows or decreases more quickly?
Exponential.
So the obvious choice there should be the exponential, right? So if that thing increases and decreases at a faster rate, it will dominate that limit. So what happens to e to the c if c approaches -infinity? So basically, I'm asking you, what does this equal? Well, that's going to be 1 over e to the infinity, right?
So 0.
So e to the infinity is a big number. 1 divided by big numbers tends towards 0. Okay, now we got to deal with this one. Same argument. The exponential will increase or decrease faster. What does e to the infinity look like? Well, it's approximately infinite. So this whole thing, everything came out to infinity. And so we would say this diverges. And again, if you plug that into a computer algebra system, right? I said x e to the x from -infinity to infinity. Notice it says does not converge. Which another way to say diverges.
So if that were a quiz or an exam question, we'd just put diverges as the answer.
I'd still want to see all the work, but yeah, you would just at the end just say diverges.
Okay.
That is the solution. All right, let's see if I can do one more for you here. A decent amount of time so that we can spend some time reviewing, which I'm sure you're all very anxious to get to. So this one here, I wanted to do this one because it has an internal discontinuity. So again, notice if I were to plug in x equal 1 in the denominator, my denominator would go to 0. And that 1 falls in between my bounds, right? 0 and 33. So I need to rewrite the integral as the limit as c approaches 1. And I have an integral from 0 to c. And then I need to write another one starting with d at 1 up to 33. Right, so I'm going 0 to 1 and then 1 to 33 basically. So that's an internal discontinuity. Again, I'm going to solve the integral itself. So I have integral dx, fifth root, x minus 1. This is a u sub. And it's going to be just the fifth root of u, or u to the 1/5. So integrating that, you add 1 to the power.
Would it be negative 1/5 power?
Yes, sorry. Add 1 to that, it'd be 4/5, right? And then you times by 5/4. We'd have plus a constant. But again, we're only concerned with the u part. That'd be 5/4 x minus 1 to the 4/5. So I can come back over here. And plug in. I'm also going to pull the 5/4 out in front of everything so I don't have to constantly keep writing it. All right. So that's everything plugged in. So what happens for this first piece as c approaches 1? So this should go to 0. And same thing for this one, right? And we should get 5/4 times. So 33 minus 1 to the 4/5, that's 32. 4/5. And then we've got minus a negative 1 to the 4/5. So can we simplify that? Well, the fifth root of 32 should give us back 2, right? And then 2 to the 4th would be 16. What about that -1 to the 4/5?
Would it just end up being +1?
It'll just be 1, and then there's that minus sign already, right? So that's what, 75/4?
I have a question. Before you evaluated the limits to be 0, would they have canceled out anyways?
What do you mean?
So like you have the limit as C approaches 1, and then you have the limit as D approaches 1, but you're subtracting that. Would they have canceled out?
In this case, sure, but in every case, I wouldn't say that, right? Because
Okay.
we're doing 1 in this case, and it's a linear function, so it acts nicely for us. If we were doing, say, approaches 0 and we had 1 over x, for instance, or 1 over c, that would cause problems in that
Okay.
case. So
Okay,
you
thank
can't
you.
always just say, oh, they're opposite signs and they look the same, so I'm going to get rid of them.
Okay, thank you. Oh, that makes sense, yeah.
So I'm just going to check myself here. It's been a while since I did this one. I think I usually let the students do this problem. So this is 1 over the 5th root and we're integrating from 0 to 33. I don't know why the Mathematica can't handle -1 to the 4/5. It doesn't like it. But it's 75/4. And you can also do this on your FNINT function, right, on your calculator to check and make sure that that works out. So I'm going to leave these other ones here if you guys want to work on them. Any questions about improper integrals?
So we would state that one is converging.
Yes, if it comes out as some number, I always say if it's something tangible, like something we understand, meaning 5, -2, that sort of thing, 1,000,000, right? That means that it converges. It diverges if you get something like infinity. Sometimes you'll see something like infinity minus infinity, stuff like that.
Yeah. And will we get points off if we don't say converging?
If it comes out as a number, you don't have to say converges.
Okay.
But if it does diverge, you must write that.
Okay. Thank you.
Mhm. All right, so I'm gonna go ahead and I am opening up the rest of the period for you guys to ask any questions that you have from the review. I can work on them. I prefer if you guys kind of, showed me what you did, ask questions, things like that. We can always pull up a whiteboard. You can work out the problem, or at least you can maybe dictate and I can write for you. So what problems from the review were you confused on?
I got stuck on 14 and 15. So like I hit a point, like I hit a wall where I wasn't sure how to approach it from there.
So let me go ahead and pull that up real quick. Come on. All right, which one did you say again?
14 and 15.
Okay. 14.
So I started with the like substitution where the square root of x squared minus a squared equals, where x equals a secant theta. And I ended up with dx, or x equaling 2 secant theta.
Okay, let me just make some room here. All right, so you let x equal what?
2
said?
secant theta.
Okay. So dx
Um,
is what?
2 secant theta tangent theta.
Okay.
And I actually think I realized what I did wrong because I didn't do the dx at all.
Didn't plug that in, right?
Yeah, yep. So I just ended up with everything in the denominator and I wasn't sure how to approach from there.
Let's just see what this looks like.
Yeah.
This is going to be 2 cubed, a secant cubed. And then you're going to have secant squared minus 1. That's tan squared. So you're going to get a 2 tan out of that radical, right?
Yep. Yeah.
And then that's not so bad in terms of these go.
Mhm.
One of those goes. This one actually turns out really nice, I think.
Yeah.
Because you get 1 over secant squared. Secant squared is equal to,
Tan.
well, you could replace that, but that would probably make it tougher. I was thinking more the lines of 1 over secant is equal to cosine.
Oh, okay. So would it be 1 over cosine squared?
Should just be cosine squared. Because it's already 1
okay,
over
so it's going,
secant
okay.
squared.
Yep, that makes sense.
And then we should know that we can replace that with our power reducing formula. And we've done that integral quite a bit of times. And theta was related to secant x over 2. So this is going to be 1/16 inverse secant x over 2, right? Because again, the only time you can use that is when theta is by itself. And then sine of 2 theta is 2 sine cosine. And then it's got a 1/2 in front, so 1/2 times 2 would cancel. And we just need the representations of sine and cosine. So we would need our triangle. Secant was x over 2, and that is the hypotenuse over adjacent, right?
Yeah.
So then this side would be x squared minus 4, and that better match what we had. It does. Sine of the angle is going to be the square root over x. And the cosine is going to be 2 over x. So it should look like that. Hopefully I didn't do that too quickly.
No, that was good. Thank you.
All right, any other questions that you'd like me to go over? You can also ask, quiz questions if you like. I know not everyone got perfect 10s on all their quizzes.
Okay, I know. So just a question. I know I definitely messed up with that when the theta's by itself for the inverse function. Like you said that you could substitute in by itself, but I know with that problem, I had like started kind of confusing myself and I ended up plugging in the inverse inside of like the other part as well where I saw the theta. What should I have plugged in there instead?
Instead of plugging in the inverse secant here, you need to replace sine of 2 theta with this relationship.
Okay. Okay. Yes, that's where I got confused. I kind of was just at a point I didn't know what to do, and I knew to do the theta by itself. So I ended up just plugging it in that other spot too.
So always try to, if you see anything that looks strange, like a sine of 2 theta, you always want to reduce it down to your basic trig functions, sines, cosines, tangents, stuff that you
Okay.
can actually read off of the triangle.
Okay.
All right, any other questions? So I can say, at least from the review, I would focus on problems 4 through 23 the most. That's where you're going to get like I said, the test is almost all integration. The only other, then you should make sure you know how to do your trapezoid and Simpson's rule. Table of integrals, not super important. Could potentially be the bonus.
I know that I missed one of the natural log rules in my integration one of the quizzes. Could you review a few of those rules or those rules?
So you have natural log of a plus natural log b is natural log of a times b. If you subtract them, it becomes a division. And I think the last one is if you have a coefficient in front of the log, right? If it's a times the natural log, you can make that the natural log of b to the a power.
Okay, thank you.
No problem. Did that answer your question? I hope. I'm not thinking of any other ones off the top of my head.
Yes, yeah.
Not necessarily related to the review, but what were your office hours again?
They are technically, I think I had 9 to 11 on Monday and Friday.
Okay.
But if you really want to, or you can't make those times, then you can just send me an email and say, hey, can you meet with me, this time on Friday or something.
Okay, thanks.
So obviously in this case, we have the rest of the day today that you can set up a meeting with me.
Okay.
So if you guys have no other questions, I have no problem with finishing early today.
Could we go over number 10?
I suppose so. Get rid of some of this stuff here. All right. So I am thinking we might be better served if we break off a secant and a tangent. And that'll get us both even numbers of secants and tans left behind. Which is good because the Pythagorean identities all have that relationship where it's even powers. So that would mean that this is du, which means u would have had to have been secant. And then we've got secant to the fourth. So that's just going to be u to the fourth. And tan squared can be replaced with a combination of secants. So secant to the fourth. Tan squared is the same thing as secant squared minus 1. And so it looks, come on. I don't know why this bar appeared on my screen. Now it disappeared. All right. So this integral, this integral then would be u squared, or sorry, u to the fourth. Right, that's secant to the fourth is the same thing as u to the fourth. Then we'd have u squared minus 1 du. And then from there, it's fairly simplistic. It's u to the sixth minus u to the fourth. Integrate. It's u to the 7 over 7 minus u to the fifth over 5 plus a constant. And then just plug u back in.
Okay, thank you.
Was that adequate? Did I go too quick, too slow?
That was fun.
I think that 15 is completing the square. Could we go over that one? I think I just feel more comfortable if I saw another example with completing the square.
Nah, I don't feel like doing that one.
Okay, perfect.
I'm kidding.
No, I know.
Let's see. Just find a new page here instead of keep pushing everything downward. All right, see that problem? Okay. So let's see. So yeah, this doesn't factor nicely, so we can't get it out of the radical. So completing the square is probably our best option. If we would take the 4 divided by 2 and square it, that would give us back 4, right? And so if I add 4 and subtract 4, that should get us what we need. You could have also noticed that if I had 13 and I needed to introduce a plus 4, I could just take 4 away from it, which is the same thing as what's going to happen here. So this factors, right? Because we used completing the square, it's going to be x plus b over 2 squared. So that's going to be x plus 2 squared. You can always quickly check yourself to make sure that makes sense. That would return x squared plus 4x plus 4, so that looks good. And then negative 4 plus 13 plus 9, right? So now my integral is this. And if you really want, you can let u equal x plus 2. Du would be dx. Now, given the fact that we have the table of integrals, right? If one said, now use the table of integrals, this would be easy, right? We could just look that up, and I think it's going to be in probably the 25 range, somewhere in there. But let's say we don't have the table, and so we've got to integrate this now. So this looks like another trig sub at this point, right? So we need to make another substitution. I'm going to let u equal. Now we've got plus, so I believe this is going to be tangent that we want. So we can do the triangle right off the bat to make sure. So tangent is opposite over adjacent. That means the hypotenuse would be u squared plus 3 squared, and that looks good. So that's the correct substitution. And then we need du. So that'd be 3 secant squared d theta, right? So plug everything in. And simplify. So it looks like you'd end up with 3 secant theta down there. Oops. Not mean to put that d theta. There we go. And if that's the case, we would get rid of these and that, and we'd be left with this. Anybody know what that is off the top of their head?
Would it be sine theta plus c?
Unfortunately, no. It would be great if it was that simple. This one is natural log of, I believe it's secant plus tangent. So that's an integral that if you ran into it, I would say, hey, remember this, because that's not one that's easily solved for. In fact, you kind of have to know what the answer looks like in order to easily solve it. You have to multiply it top and bottom by secant theta tan theta, and you get a du over u situation, which results in the natural log solution. So anyhow, once you have that, you just need to plug in. So secant is going to be that's related to cosine. So hypotenuse over adjacent. And instead of u, we can plug back in x plus 2 and tangent's going to be u over 3, right?
Thank you. That really helped. Thanks.
You're welcome.
So where did you say people would have like originally learned completing the square? In what class?
Completing the square is something you should learn in algebra class. So
Oh,
that could either be in, I guess, late middle school, early high school, or late high school whenever you had algebra, or it could have
early
been
middle
college
school.
algebra at the at the college level.
Yeah. Okay.
That is typically when you should learn it. That doesn't mean that you did.
Yeah. Even if I did, I haven't had algebra in like 15 some years, so it's like all rusty for me.
It's kind of one of those things that you spend like, I don't know, 10 minutes on in algebra class, I guess. So it's easily forgotten.
So for that problem, would we be given the integral of secant theta equals the natural log of all that? Or is that something we'd have to know for the exam?
Yeah, I think that I had mentioned that if you run into that, it would be something like hint integral of secant equals this.
Okay. Okay, thank you.
which is good in two ways. One, you don't have to remember it off the top of your head. And two, when you're doing the problem, if you don't end up with a secant at some point, you should be thinking to yourself, uh-oh, I did something wrong. So how about we do this for a second? Let me clear my drawings here. If I can figure out where to do that. I should have it just clear all. Not seeing why is there a drop-down menu if it won't open?
Can you like right click on select? Will it give you options to select all? Hmm.
My computer's losing it. Like it starts to show something and then it goes away. All right, I'll just do this. I'll just reopen it. So what I wanted to do was just go through these integrals here and ask you a random one, and you tell me what technique you would use to solve it, which is a pretty good skill in its own. So number 6. Someone tell me how you would solve that. Using what integration method?
Integration by parts.
Okay, and how many times do you think you'd have to do it?
Two.
That x squared, right? If you let that equal u, which is hopefully the logical choice.
Yeah.
In that case. And that one's a little strange because it goes against, well, I guess actually you could use the log for that one. And then I think you'd only have to do it once, but if it's, let me give you a different example. Let's see. Number 4, x squared cosine x, that one you'd have to do twice. If it was x to the 5th, you'd have to do it 5 times. Right, because the algebraic function comes before the trig function. For number 6, the log comes first. So in this case, if you do that, derivative will give you 1 over x, and then the other form will give you x cubed, which will be an integral you can solve. So you only have to do that one once, actually.
Okay.
Does that make sense to everyone?
Yeah.
So basically, if the u for the biparts is raised to a power, we should expect to do it that many times.
If it's an algebraic function, yes. Let's see. How would you solve 18?
Partial fractions.
That's a partial fraction decomposition. Okay. What about 13? How about somebody else chime in?
Trig substitution.
That's a trig sub, good. And what about 22?
Improper.
It's improper because we have a infinite bound, and then the integral itself is just a basic u substitution. What about 7?
For 7, I think I did by parts, where you let dv equal dx.
So that's one of the ones that's by parts, but we called it not apparent, right? Because there's only one function, and you do let dv equal dx. So good.
Oh, I'm sorry, I missed number 22. How would you solve that again?
That is an improper integral.
Okay.
So you would need to use your limits for that, and it's just a basic u substitution.
Thank you.
What about 3?
This was the one where like I broke it up into when x was greater, like so when x equals 5/3, then you have to change like the signs, like when it's greater than 5/3 and when it's less than 5/3, and treat them as two different integrals.
So that was a real special case, right? Because of the absolute value. You got to break it into 2 pieces. It touches the axis at 5/3. So you'd have 2 integrals, one from 0 to 5/3, another from 5/3 up to 3. And the equation of the line for each section has opposite the sign. So good. Let's see, what else? So we already did 14 and 15. I think 8 through 11 are, they're, we don't need an explanation. They're trig integrals, right? They all have trig functions in them. So I think we've done one of each. So that was good. Seemed like you guys have an understanding of looking at an integral and understanding how to attack it, which is half of the battle. Especially when you're not in this class, right? It's probably the biggest skill that I could teach you is to look at something and understand what you need to solve it. You may not remember the technique, but if you remember what it's called, then you can go look it up. So, right, not everybody's going to stuff all this stuff in their head and remember every single thing they've ever done. All right, any other problems you would like me to go over? I think the only thing we haven't done yet would be maybe a by parts, or I think maybe if you guys want, I would suggest trying one of these trapezoidal and Simpsons rules by yourself. We only did the one example in class, and I have not had a chance, obviously, to grade your quiz as it was due this morning before class. So maybe it would be a good idea for you to try that.
I just had a question with the Simpsons rule. I had noticed that n has to be even for it to work. Is there ever an instance where it wouldn't be even, or should we always choose an n that is even?
So for problems that I give you, n better be even.
Okay.
If you are, now obviously, you're not always going to, you're going to, if you were to do this in the real world, you'd be doing this on your own and you'd be choosing n. And in that case, you still need n to be even.
Okay.
The reason for that is, remember that the coefficients were 1, 4, 2, and then it repeats, and then it has to be 4, 1 at the end.
Yeah.
If you had an odd number, those coefficients don't match up properly.
Right. Yeah. That one before the end isn't going to be 4. That makes sense.
I had a question about both of those really. Like, so you know how we're supposed to do like our own calculation and compare it to what we get from using the math function in the calculator?
Mm-hmm.
Is there an expected like error percentage or something that we're shooting for?
Again, that
Because
would
like I wasn't sure if I did it right for the quiz, so I put the error percentage because I wasn't sure if I was close enough or not to what I was supposed to be. Like I just wasn't sure how far off of the actual answer I was supposed to be.
so again, for the class setting, it's just a matter of how close are you. I'm not asking the question, you must be within this range. But if you were to use the technique, outside of class, then you might be giving yourself that restriction.
Yeah.
Does that make sense?
Yeah, that makes sense.
Does the percentage error go down the bigger the n, or?
So yeah, if you think about it, right, the bigger the value of n, the more areas that you're taking, and more importantly, the closer that you can fit the curve. Right? If you
That makes
take really small values of n, or sorry, really big values of n, you're taking really small rectangles or trapezoids. And so each one of those will fit the curve more accurately as n gets larger.
That makes sense.
So yeah, obviously, if you were trying to get a better percent error, then you would just need more values of n or higher values. These are all good questions, by the way. They seem to, at least from my perspective, asking those kind of questions means that you understand the technique and you're taking it a little bit further. So we've only got about 3 minutes left for class. If you have something you want to see, I could do it real quick. But like I said, I would suggest maybe trying one of those. That way, if you have a question about it, you can ask me before we go. If anybody wants to set up a meeting, shoot me an email. I can try to meet with as many people as possible. Obviously, there are not 23 hours left in the day, and there are 23 of you. So, if you really want an hour or something, then let me know. But I'll do my best to satisfy the group.
Are we allowed both sides of the note sheet?
Yeah, you can use the front and back.
Thank you.
I have a question. So you told us that basically from like 1 through 3, 5, they're all the integration. And you said that we're gonna expect to use like each type. Should we also expect to use multiple types? Like, you know how sometimes you can use something and then end up having to do integration by parts still. Should we expect to see stuff like that as well, where it's multiple in one problem?
Off the top of my head, I don't have them all worked out. So I don't know exactly how they turn out. I can say for sure that the majority of trig substitutions typically get you back to a trig integral. That's just kind of how they work out. So that's a potential problem where you'd start with one technique and have to use another. But I'm certainly not trying to give you an integral that requires you to do 3 different types of techniques just to get to an answer.
Yeah, that was the question. That's all.
I did give you one, like I said, that it's going to be, it tells you specifically use substitution, and then it tells you again to use another technique, specific one that's given. So, there's 2 ways you can solve the problem, and it just wants you to prove to yourself that you can do it both ways and therefore get the same answer.
Okay, thank you.
Mm-hmm.
What's the point distribution of the questions? Like 10 points?
Oh man, now we're getting down to the nitty gritty, aren't we? Off the top of my head, I don't know. There's some of them that are 10, some are 15. I think the one that's got the two types of, the one I just mentioned with the U sub and stuff, that one could be 30 points. Right? There's only 7 problems, so it's 100 points divided up amongst 7 problems. The bonus problem is worth 10 points. Unless, of course, I decide to change it, and then it might be different.
Okay. Thank you.
All right, guys, it's 11 o'clock. Do you have anything else pressing that you'd like to ask? Concerns, questions, complaints, derogatory comments? You're going to go file your resignation right now from Calc 2. All right. Well, I'm going to go ahead and stop sharing. I'll stop recording.